And now we have a nice plot. What is shown here is often called optimization landscape or fitness landscape. And this is simply a metaphor or some depiction of what's going on in optimization. This is the space of solutions. And you can see this X and Y, and this would suggest and would actually fit perfectly if you had this mathematical formulation of cost equals some function of X and Y. So this is what this function or this formulation could be used to generate exactly this picture. But I mentioned that this is a metaphor because this XY plane doesn't have to be a plane of XY pairs like real values. This picture is supposed to show this plane as the space of all possible solutions. So you can have all those TSP rules or SAT evaluations of variables, all those chess programs, lying here, or all those assignments of pictures to text. We talked about LaTeX, for example. So this is all the solutions, like balls on a plane. And then each solution has some quality, because now we are speaking about single criterion optimization, so each solution has only one evaluation value, one quality value. And actually this vertical axis says cost. It doesn't say gain, it says cost. And cost means that the lower the value, the better. So maybe if you thought in a different way, now you have to switch. The lower the better. So this is the solution with the highest cost. We would need to see what is this solution, this XY. There is some solution here and it has the highest cost. And we also have those black circles, what they are supposed to show. Any ideas? What are black circles? Like somebody was hungry and ate parts of this plot. Yeah, these are constraints, like mice, maybe mice. These are constraints. So this means, it may be misleading, because for constraint solutions, we usually are able to calculate this value, this quality value. So we could show them, but maybe in a different color. But we still would have some shape, probably here. We don't have this in this plot. So these are solutions. Actually, these are not the solutions. Solutions are here, below those black circles. These are solutions that we want to be excluded from our set, for whatever reason, as I mentioned. Okay, so where is this global optimum? Global optimum is here. So here would be some XY or some solution which is the best. Let's imagine those three basic algorithms. How would they work? We know that the full search would simply search through all this landscape and find the best solution. Random would sample randomly. Heuristic is like this some approach based on human knowledge. So it would be like, after many millennia or hundreds of years, humans learned that it is quite good to have x around 5 and y should be more or less half or 1/3 of x. Well, it's like approximate human knowledge that usually works, because usually we get quite a low cost. Nobody cared to search through all those possibilities, because humans were somehow not obsessed with the best solution. They are very satisfied when they are somewhere around here. Okay, so now you could have the question, because I said that this is a metaphor, right? And it is. This chart indeed is just like for your imagination. But you could ask, what is the shape real optimization landscapes for real practical problems, like for TSP. First of all, it's difficult for TSP to draw such a nice chart because you cannot arrange TSP roots. We know that TSP roots are permutations of elements. So it's hard to arrange them in a two-dimensional space because you have some other space in permutations and you would need to squeeze it into 2 dimensions. It's not easy. So that's the first thing. But still, you could think how this landscape looks for practical optimization problems. So this is one kind of a landscape. This is another kind of a landscape. So this one could be like maximization. We are looking for the best solution, and the best is at the top of this spike. This is minimization. So the globally minimal solution is probably somewhere in the middle, but we don't see it. And this is again minimization. And we actually don't really know where the minimum is, probably somewhere in these darker regions, which seem to be lower. Would you be able to assign difficulty to those problems? Like which of them seems the most difficult and why?
Pause the video and try to answer this question.
So what would be some features of this landscape which would reflect difficulty? How would we call this feature of the landscape? Or why is the first easier and the last most difficult? Can you name it?
Maybe too many peaks.
Too many peaks. So the number of peaks.
Number of highest
and the peak. How would you define a peak? A peak would need to have something to do with this locality. So it would be like a solution which is surrounded by. Maybe it would work. Yes, it works. Okay, so you can even play with some program that will display, and you can even enter your own formula and run some algorithms. Oh, so okay. So this is the last slide of this lecture. We have 2 landscapes. This one looks easy, this one looks difficult. It's like a smooth blanket, and this is like a very spiky landscape. So you would say that this is very difficult and this is very easy. But what if I told you that those 2 landscapes are actually more or less the same? Because what actually causes the landscape to look in a particular way? What would you need to do to transform one into another?
Change Z.
Yes, but you are not allowed to do this.
Redefine some values as and so we can redefine X.
Yeah. I mentioned that this plane is a space of all possible solutions, not necessarily 2 real variables, but a set of all possible solutions. So I mentioned those balls, like each ball is one solution.
We can put those solutions in some order.
Yeah. So you remember when I was explaining the difference between a set and a space, and a set is like an ordered set, and a space has some topology. So you could simply rearrange all those balls in a different way, and you could get a very complex problem from a simple problem, and you could get a very simple problem from a complex problem. You only need to be smart with how do you arrange those solutions in those neighborhoods. Okay? So I'm showing this because this is very important in optimization, and most people don't speak about it. Most people are obsessed with algorithms, optimization algorithms. And of course, it's good to have an efficient algorithm, But note that this optimization problem would be easy for any optimization algorithm, and this would be hard for most optimization algorithms. So if you have some smart way of rearranging those balls and rearranging those solutions, so you build a better space, so to say, a better space, a better relation, this topological relationship between solutions, then you should always do this. And how to do this? You always need to think to place solutions nearby which have a similar fitness or this evaluation function. So it's very straightforward, actually, quite intuitive to do this. But you can break any problem into something very difficult. What is this mapping? This mapping is exactly what I mentioned. How to arrange those solutions. This mapping is the mapping between the arrangement of solutions and this fitness value on this or this evaluation function. So nothing to be said more about it. FD correlation stands for fitness distance correlation. And this is the formal measure that will tell you exactly how smooth is this landscape. And what is the fitness distance correlation? Fitness is the vertical axis, and the distance is the distance in this space of solutions. So you can take like 1,000 pairs of solutions, calculate the distance in the space, in this original space of solutions, and calculate the difference in fitness. So you calculate the distance here on this xy axis and the distance here on this vertical axis, and if they correlate, then it means that the landscape is smooth. If they don't correlate, if the correlation will be low, then it means that there is no correlation between the distance in this space and the distance in the vertical axis. Do you see this? It's quite simple. So you can use a mathematical formula, a correlation, to actually tell you how easy the problem is, but you need to implement some measure of distance in this space of solutions. Because unfortunately, you need to evaluate similarity of solutions. So unfortunately, you need to provide, for example, some measure which would evaluate distance between one chess program and another chess program, on one TSP route and another TSP route. Because this is our solution, right? So this may be tricky. So we know fitness distance correlation. What is GC? GC stands for global convexity. Global convexity. And global convexity is a very nice feature. It says that in practical optimization problems, in real life optimization problems, this landscape looks more or less like this. If we are minimizing. So looking from the distance globally, if we are minimizing, there is some place in this huge space where when solutions are more and more, the quality increases and they are similar to each other. So unfortunately we have those small pikes everywhere, but there is some location or some place in this huge space when usually solutions are good. But it all depends on you. It all depends on how you arrange those solutions in the space. What this global convexity says is that in most natural orders, even if you don't think a lot about how to arrange those solutions, you will see this property. And this is good for optimization because it means that at least we have some clues where we should go when we are looking for the best solutions. And finally, no free lunch, NFL, no free lunch. No free lunch is a very famous phenomenon. Did you ever hear about no free lunch?
No free lunch means that when we do something better, we also do something worse.
Yeah, it could be understood like this. I will give you an example of compression. Have you ever used zip or rar or some of those programs to compress files, right? So why do those programs actually work? How it is that they produce smaller files? because in most practical files that you compress, there are some regularities. And those regularities can be compressed because they repeat. So when you take a natural text, a Word document, things like this, they will be compressed. But you could imagine, unfortunately, a much larger number of files with random contents, like random bytes, and they would not compress. If you tried to compress a random stream of bytes, after compression it would be larger. And this is the no-free lunch. If you considered the set of all possible files with all possible contents, there would be like, let's say that this square represents all possible files that you can generate, for example, of length 1 megabyte. This tiny dot would be the proportion of files which have regularities with them and can be compressed. And the other part would be those random contents. So there is a higher number of random files which you couldn't compress, and what you gain on those regular files, you actually would lose on those random files, and it balances out. So the same works for optimization, and no free lunch in optimization. We will learn a number of optimization algorithms, and they will work because practical problems have global convexity. So we are lucky that in our world, optimization problems have some structure, have some regularity. They are globally convex. So it makes sense to learn local search, for example, or some improved local search algorithms. But you could imagine a much larger number of optimization problems where none of those algorithms would work, because the landscape would look like this, but completely random. So this fitness distance correlation would be zero, so to say. There would be no correlation between similarity of solutions and their fitness value. So you understand why no free lunch in optimization? There is a larger number of problems which are completely random and hopeless, but fortunately, in practice, we do not encounter them.